Hey everyone, welcome to Chemistry 40 with Dr. Carroll. This is Unit 3, Lecture 2. Let's get that written in here, right here. Unit 3, Lecture 2, all about chemical kinetics. Today we start with the focus collision theory. If you want a chemical reaction to happen, you have to have things collide with other things. If you want a physical reaction to happen, you have to have that too. So the collision theory states particles must collide in order for a reaction to happen. But not all collisions will give you a reaction. You can have collisions where you don't get a reaction, just like you could have one car hit the bumper of another car really slightly and not cause a dent that MPI would notice. So that would be an ineffective collision. There's a big dent, yeah, that's an effective collision, and you'll lose your deductible. So, to be an effective collision, you have to have that energy greater than the activation energy greater than that or equal to activation energy, fine, and you have to have the proper orientation, the proper alignment to make it happen. We've mentioned a bit about this in our previous lecture. Now we go into more detail. Let's say in this example we've got ozone, which is O3. It's converted to oxygen gas and NO2 gas by reacting with nitrogen monoxide. So here's nitrogen monoxide, here's ozone, here's nitrogen dioxide and O2. Now suppose it has enough energy, but not the right orientation, then you won't have things happen. So here we have oxygen and oxygen hitting each other. So this is an O and this is an O, and they hit each other, and they don't, so there we go, let's get those arrows better, bang bang, they don't cause transfers of atoms, you don't get bond breaking or bond forming, they just bounce back. That's over here, so no reaction happens. Here I flip the molecule of NO, so the nitrogen end hits oxygen, and then that let's see what happens here. The oxygen goes to the nitrogen. This is the oxygen. It goes to the nitrogen, and so I get NO2, and I get an oxygen. It changed its angle, by the way, and I get an oxygen left over. So O2 left over. So you have different modes of attack. One is an oxygen attack, the other is a nitrogen attack with reference to the nitrogen monoxide. And both of these things happen. As chemists, we try to use temperature, other techniques, catalysts, all sorts of ways, lasers, to make the odds in our favor, to stack the deck so that more often we'll have the nitrogen of the nitrogen monoxide attack the central oxygen and ozone than the oxygen and nitrogen monoxide attack the central oxygen and ozone. So that's what we mean by orientation. We'll see some other examples as we go through. Just a reminder about activation energies. Not only do particles need to collide with the proper orientation, they must also collide with enough energy. Chemical reactions involve the making and breaking of bonds which require energy. If colliding particles do not have energy greater than activation, they will not produce a reaction. So that's just a review statement there. The minimum amount of energy required for colliding particles to produce a chemical reaction is called the activation energy, and the larger the activation energy, the longer the reaction takes place. Activation energies are always positive values, so don't quote an activation energy as a negative value. It's always a positive value, and we can talk about both forward and reverse activation energies. Okay, remember we said that before. If you have reactants, go through the activated complex to products. Forward activation energy is left to right, reverse activation energy is right to left. Because as the reactants form products, the products are going to start smashing into each other and go back to reactants. How much they go back, to what extent, well, that is a discussion for our next chapter on equilibrium, chapter 4. Let's do a bit of a sidebar here on heats of reaction. Just as a bit of review before we look at more orientation. So the rate of reaction is determined by the height of an energy barrier that the particles must cross in order that they are converted into products. This activation energy is the barrier colliding particles must overcome. And you can lower that barrier by using a catalyst. As the particles collide, they form an unstable high-energy particle called the activated complex. Let's not use the word particle there. Let's use the word system. I like that better. A unstable high-energy system called the activated complex. The energy required to produce the activated complex is the energy of activation. The activated complex has a maximum amount of potential energy, but exists only for a small instant of time. Okay? And so it's the arrangement, most unstable arrangement of colliding particles. A complex really is a collection of things, right? The Polo Park is a shopping center complex. There are various stores located in Polo Park. Now, if you didn't hear before, enthalpy, or H, is the heat content or total energy absorbed by the particles in a system, and it can be related to energy. Very close. The energy released or absorbed is called the enthalpy or heat of reaction. So delta H is the H products minus the H reactants. If delta H is negative, the products have less enthalpy, energy, than the reactants. So heat flows out of the system, causing the reaction vessel to feel warmer to the touch, and it's called an exothermic reaction. So if energy is released in the form of heat, you have what's called an exothermic reaction. Okay? Combustion is an exothermic reaction. Energy is released. If delta H is positive, heat's absorbed. Evaporation is an example of an endothermic reaction. So heat's absorbed into the system because the products have more enthalpy than the reactants. The vessel feels cooler as energy is absorbed from the surroundings. So this is called endothermic. So we can put that together into two important equations, which you should memorize. Delta H is the potential energy of the products minus the potential energy of the reactants, but it's also, as we'll see from our potential energy curves, the forward activation energy minus the reverse. So I'm going to write that on a piece of paper here, so I'll remember it. Delta H is potential energy of products minus potential energy of reactants, and it's also equal to EA forward minus EA reverse. Okay, so that's page 14. Now let's look at some two orientation examples. Let's say we want to form carbon dioxide. So you want carbon in the middle, right? And oxygen symmetrically on either side. So we're going to have carbon monoxide be attacked by oxygen to get carbon dioxide and O. So suppose we want that to happen. We can have a head-on collision where the oxygen end of CO attacks the oxygen end of O2. So we're going to start to form an activated complex, and then we're going to form COO plus O, or nothing at all. But if we form COO plus O, that's not what we wanted. That wasn't our desired product. So that would be an ineffective collision. If instead we flipped the carbon monoxide around so it was the carbon end of carbon monoxide attacking the oxygen of O2, but these are just ball and stick diagrams. I'm not using the single, double, or triple bond, just to show things smashing together. Here you start to form a bond between the carbon and oxygen. You have carbon monoxide with O2, and this bond starts to break, and so you get OCO plus O. So again, the end of the molecule that does the attacking is important. That's the orientation, the directionality, and that's important. So you want to try to find ways so that the carbon end of carbon monoxide attacks the oxygen of O2 more often than not. Sometimes you can get side-on collisions. Here's hydrogen and iodine going to form HI. So they hit each other together side by side. So I'm putting less dots here, meaning a bond starting to form, and more dots here, so a bond starting to break between the hydrogen and iodine. So that collection here is my activated complex. And some of in the system, some breakdown will go back to the reactants and some will go to products, HI and HI. So this is a nice effective, efficient collision, assuming enough energy by having them hit together side by side. If they don't hit together side by side, well, they might not hit each other at all, then there's no reaction. If they collide head-on, well, so you could start to form an HI. So that's one HI molecule, but you still have a separate hydrogen iodine, so they would have to collide again after, so it'd be another step. So you would end up with the two HIs eventually, but that's two steps rather than one. So it's effective, but the rate is lower. The rate of production is lower because you got an extra step. So that, if you have control, that would not be the preferred method to make your hydrogen iodide. Okay, so and you can do a Google on computer animations of orientation in creation of products and activated complexes to see more examples of orientation. One thing just throw in here, if you just have a molecule and it just breaks apart on its own without hitting anything else, maybe it's releasing some energy from some excited state, that's called unimolecular. Two-body interactions are the most common. Those are the ones we've seen today. That's called bimolecular. Three-body interactions, three things hitting each other at the same time. You might think that would be called tri, but it's not. It's called termolecular, just like you think about tertiary tertiary healthcare, secondary healthcare, primary healthcare. Tertiary hair care would be maybe using like curlers or something, or some hairspray. Oh, I made myself laugh. Three-body interactions are not as common as two-body interactions. Four-body interactions are very rare. You don't see four things colliding all at the same time. Some students say, oh yeah, well, there's a big collision on the highway and there's a 20-car pileup. Yeah, but that's usually just a series of two-body collisions, right? A chain reaction. It's not four bodies hitting each other at once. Okay? So, let's spend the next section of today's lecture looking at potential energy profiles. I know we looked at them before, but let's look at them a bit more detail so you really become an expert on this, because definitely on a test, on a quiz, you have to be able to draw these things, and I can also give you these things and then you have to interpret and read off the drawing. So you have to know things upwards, downwards, backwards, and forwards, just like reactions happen. Potential energy profile represents the energy change that occurs during a reaction. So here we have, this one's going to be exothermic because products are lower down than reactants. There's my forward activation energy. I don't have any catalysts here. And yeah, activation energy forward. Let's keep all that together. So that goes here. And then my reverse activation energy is here. So you see that EA forward minus EA reverse gives you this part here, which is delta H, which is negative. Or potential energy of the products minus potential energy of the reactions also gives you delta H. The activated complex lives at the top of this curve, and every reaction is a different shape curve. If it's exothermic, the product's always less than the reactants. How high it goes, well, that depends on the activation energy. Okay, so we've said all that. Endothermic reaction. There we have the products are higher up than the reactants, so delta H is positive. Forward activation energy from the reactants to the top of the hill, activated complex living at the top of the hill. Products to the top of the hill, that is my reverse activation energy. So in endothermic, reverse activation energy is less than forward activation energy, whereas for exothermic, reverse activation energy is more than forward activation energy. Okay, then there's this thing about roller coasters. Beginning of a roller coaster ride is a long, slow uphill ride. Energy is expended by motors in the effort to get the cars to the top of the first hump. It's like molecules coming together, trying to get through the electron density envelope of the other molecule. Once the cars reach the top of the first hump, it's all downhill. The cars have enough energy for the entire ride, regardless of the number of ups, downs, twists, and turns. So here's an example using actual molecules here. I got hydrogen and oxygen. I got hydrogen, another hydrogen, and there's an oxygen. They're my reactants. My products are water and water, and then I have here oxygens, hydrogens, and hydrogens all coming together, starting to change their geometries and breaking apart to give you 2H2O. This is an exothermic reaction. Now the hydrogen and oxygen, they can live. You can have hydrogen and oxygen together in a flask without exploding because you don't have the activation energy yet. If you spark it, oh, then it explodes because then you have provided through thermal energy enough energy to make the activated complex and therefore products. Okay, the activation energy is high because these are covalent molecules, so it takes more energy to break those bonds. The activated complex doesn't last long, but it has to be formed in order for the hydrogen to burn. And it's an exothermic reaction. Here's another one on page 18 with, what is this, bromoethane to form ethanol. So this is exothermic, and oh, we have some numbers here. Is that it? Okay, fine. Let's just take this as our 0. When in doubt, if you aren't told otherwise, we'll take our reactants at 0. So from 0 to 88.9 is my forward activation energy. I'm having my OH attacking the Br-, usually activated complexes are written like this, and then we swap and we kick out the bromide. So my forward activation energy is 88.9, my delta H is 77.2, so I can get my EA reverse. Okay, oh, I forgot my calculator in the other room. That's okay, let's get it here. It's going to be EA reverse is going to be EA forward minus delta H. So 88.9 minus a minus 77.2. So 88.9 plus 77.2, 11, 16, 166.1. Is that correct? 80. That's like 90 and 80 is 170, a little less. So 166.1. So that is EA reverse in this example. Okay? And the potential energy of the products, if I decide that 0 is my reactant, and that doesn't have to be a choice, but it's often a good choice, then my products are, potential energy of products is negative 77.2 kilojoules. Okay. Sometimes activation energy is kilojoules per mole. Oh, look at it! Look here. I did all the number crunching right over there. So there you see it again. So, according to collision theory, in order for a chemical reaction to occur, this is just a mini summary. Then we're going to do more of these potential energy profiles. Reacting particles must collide with enough energy in the correct orientation. The rate of reaction is determined by the number of successful collisions. The more successful collisions per second, the higher the rate. Activation energy is the minimum amount of energy needed to produce a reaction, or the amount of energy needed to form the activated complex. Fine. The higher the activation energy, the lower the number of particles that can produce a successful collision. And heat of reaction is a change in enthalpy when a reaction is complete, or the difference between the enthalpy of the product and the enthalpy of the reactants. Okay. Final minus initial. Catalyst. Oh, that should have been on another page. So let's go and look at a few more practice things for potential energy graphs. So here's another example. It's an exothermic example. I'm on page 19 in the booklet. Hydrogen plus iodine. There's my side-on going to 2HI plus 70 kilojoules. Now kids get mixed up with this. If you see a reaction and you see explicitly a number associated with an energy written, if it's on the right-hand side, it means it's given off. So you're releasing energy. So your delta H reaction is negative 70. So whenever you see energy on the right-hand side, your delta H is negative. If you see energy on the left-hand side, that's endothermic and delta H is positive. So suppose the potential energy of the reactants are 0, then the products are going to be down 70 from that, right? Products would be delta H minus the reactants, so minus 70, so plus the reactants, minus 70 plus 0, so it's 70 down. And EA forward, well, I don't, oh, I didn't, okay. You're given 3 of the 5, and you got to get the other 2. So EA forward is given as 60, so EA reverse is EA forward minus delta H. So 60 minus a minus 70, 130. So once you get those 5 nuggets of information, you draw them in. So you have potential energy along the left-hand side. Always make sure to label your axes. It could be kilojoules, kcal, kilojoules per mole, kcal per mole. And so there's my reactants at 0. My products are 70 down from the reactants. My forward activation energy is from wherever the reactants are to the top of the hill. So that's going up by 60. And my reverse activation energy, well, I got 70 and another 60, which is 130. So further, a reminder, the x-axis has to be labeled. You can label it with the words reaction coordinate, reaction pathway, progress of reaction. Don't use time. That's not quite a good one to use. So use one of these 3. They're all acceptable. And then, so you draw your number points and then you just join them up smoothly. If you want to draw like straight lines going up and down, go ahead, because we don't quite know yet what slope is needed. You need a bit more, I think, grad school chem to get the slopes of these potential energy profiles. Okay, but you should be able just to draw a straight line or draw a slope if you want. Further, some kids ask, how close do you put like the P and the R along the horizontal axis? And that's information we won't know for a few years. So for now, just make sure that they're spaced enough so that you can write everything else in. Like, don't squish them too much. Use your space that you have when you're drawing your graph and space things out so you can read them and I can read them. Okay? Let's look at another one here. So we just have some general reactant going to product through an activated complex. And it's exothermic. Here you're explicitly told that the delta H reaction is minus 10 kilojoules. I could have written product plus 10 kilojoules, fine. And so you're given these 3 things here. The reactance is 0, and here you're given EA reverse. So you got to get the other things and then sketch them. So the products is delta H reaction plus the reactants. Yeah, so that's minus 10 plus 0, so the products are 10 below. EA forward, if I isolate for EA forward, it's delta H plus EA reverse. So minus 10 plus 30, so it's 20. And again, I'm repeating myself, but so what? If your activation energy, forward or reverse, is negative, you've made a mistake. Okay, so delta H reaction is minus 10 plus 30, so 20 kilojoules. So now I have all that data, and I can sketch it. There's my potential energy profile. This will be out of 8 points. So 1 for this scale, 1 for this scale, or it could be out of 2. Label 3, 4, 5, 6, 7, 8. Maybe another one just for the general shape of the graph. Okay, let's look at an endothermic example here. We've got 50 kilojoules plus A plus B goes to the activated complex, goes to C plus D. So the delta H is on the left-hand side, so that is positive 50 kilojoules. EA reverse is given, so we're going to give you these 3 as 90, and here we're going to give you a case for reasons that I've never seen a good explanation why, but sometimes you can have potential energy starting not at 0. So this one starts at 10, and so we want to get the other 2. So EA forward is delta H plus EA reverse, so 50 plus 90, 140 kilojoules, that says 140. And the products is delta H reaction plus the reactants, so 50 plus 10, which is 60. So now we have the 5 bits of information, and I can draw them in. So notice here that the reactants are not starting at 0, they're starting at 10. Okay, so the reactants start at 10. They zoom up by 140, so careful, careful. look here, the activated complex is at 150, not at 140, but 150, because the difference has to be 140. Kids get caught up on that. Don't. Understand? Don't, period. Understand how it works, please. Okay, so from the reactants at 10 to the top of the hill, 150, so my forward activation energy is 140. The products are sitting at 60, they're going up to 150, so their difference is 90, which makes sense because that was our given EA reverse. So we're all happy. That is the potential energy profile for that value. Okay, here comes another one. The reactants here now, oh, I changed the units to kcals. That's okay. Reactants are at minus 30. Reverse activation energy is 90. Delta H reaction is 100. So it's 100. Now, some of you can look at the graph first. Some students do the graph first, or some of it, to help out. So you went from minus 30 up 100. So you know your products are going to be 70. But I like to do all the calculations first and then graph. I think the majority of you will do it like that. So it's 100 plus minus 30. So the products are at 70 kcals. The forward activation energy is delta H reaction plus EA reverse. So 100 plus 90, so 190. So, if I start at minus 30, really, I just go up to 150? I don't think so. Let's look at this a bit more. That's not right, is it? I should be going to 160 because EA forward is 190. So if I start at 30, going to 150 just is 180. So that can't be 150. That has to be 160. Okay, glad we saw that. Go across there, 160. And that makes sense. And the products are 70, add 90 to that, up to the point 160 corresponds to reverse activation energy. So always double check. Okay. Oh, it's some exercises. Let's do these ones together. Why don't we? Given the following reaction coordinate diagram, what is the activation energy of the reaction? Now, if you just hear the word activation energy, you mean forward activation energy. So here's my reactants, my activated complex, my products. What is that? 80, 90, what would you say? Or 95? Let's go with 95. Okay. And so my activation energy forward would be 75. If I wanted to do reverse, okay, that's at around 37, let's say. So 95 minus 37, 15 minus 7 is 8, 58. What is the enthalpy change? Well, we went from 20 up to 37. So there's my delta H. So it would be 17, right? Okay. This is EA forward. This is EA reverse. And I want to say EA Sports. Get in the game. EA forward, EA reverse, EA Sports. And this is an endothermic reaction because my products are higher up than the reactants. Okay. Here's another one here. I got the reactants. I got my activated complex. I got my products sitting at around, what would you say that is? Fine, I'll say 25. And this is around, we'll say 250. So my forward activation energy is 150. My reverse is 225. My delta H is negative 75. So I did all that. Now let's look at the questions. What's the activation energy? Again, I'm assuming forward activation energy is 150. Reverse would be 225. Enthalpy change is negative 75. This is exothermic. Activation energy of the reverse reaction. We got that already, 225. Okay. Here we're going to sketch a potential energy curve that was represented by these values here. So I got delta H, I got EA, and I got potential energy of the reactants. So potential energy of the products is going to be negative 100, right? Because you started at 0 and your difference is negative 100. So this is exothermic. And EA reverse, watch this. I'm not going to get EA reverse first. I'm just going to, no I am. Let's not be a show off. EA reverse is going to be EA forward minus delta H. 20 minus 100 is 20 plus 100, which is 120. Okay, so do I have to go negative at all? Yeah, I do a bit. So let's go, here's my 0, here's 100, here's negative 100, there's 150. I don't think I have to go lower than that. So here's my reactants at 0, my products are at negative 100, my forward activation energy is 20, and my reverse activation energy is 120. So I really only needed to go up to 20. I didn't need to go up that high, did I? Could have just stopped here. That was a big waste of space. I could have stopped at 50 because it really just goes up to 20. Okay, sometimes it's good to do those in pencil first and then take it from there. This question 4, I don't like the wording. Some of these concepts aren't good, so don't worry about question 4. Question 5, we can try. So we're going to have EA forward is 40. So potential energy reactance is 0. EA forward is 40. Delta H is negative 10. So potential energy of the products is negative 10 kilojoules. And EA reverse is going to be EA forward minus delta H. 40 minus a minus 10 is 50. Okay, so now I think I can just go between 50 and negative 50, can't I? There's 50, there's negative 50, there's 0. Oh, watch this, I'll show off here. There's a different color. Reactants are sitting at 0. Products are sitting at minus 10. Forward activation energy is 40, so the activated complex is at 40. And reverse one is, E reverse is 50, really? 0 to minus 10. I don't think so. EA reverse is EA forward, which is 40 minus 10, 50. Products are at 0. No, reactants are at 0. Products are at minus 10. Something's odd about this drawing here. Oh, this goes from 0 to 40. 40, right. So this is at minus 10. So minus 10, 10 and 40 gives me 50. That's right. I should have labeled more data, more points. Now I will. So that's EA forward, and this is EA reverse. Okay? Some sample multiple choice. Let's do these together. The rate of reaction may be affected by each of the following except, now you can go on pause, try the answer, and then unpause. I'll count to 3. I counted in my head. Did you get the answer? The answer is the amount of energy liberated. Nature reactants, that affects the rate. Temperature of the reaction affects the rate. We've seen that. Concentration of the reactants, the more stuff we have in there, that affects the rate. Surface area affects the rate. Amount of energy liberated, we'll get that energy. The question is just how long. Kinetics tells us how long. So the rate doesn't depend directly on how much energy is liberated. Okay, question 2 is crossed out, so forget about it. Question 3, sawdust. Sawdust is blown into certain furnaces to increase the rate because you want to get greater surface area. Not a catalyst. It's not a catalyst because the sawdust gets used up. So that's not a good answer, the sawdust doesn't come back. So just you're increasing the surface area, and that gets things going. But it isn't a catalyst. Incorrect to say that catalyst changes the rate of reaction. Physical and chemical absorption are just methods in which a catalyst will work. Physical absorption is often with heterogeneous catalyst, and chemical absorption, homogeneous catalyst, not always, but most of the time, without taking part in it. A catalyst does take part in a reaction, and one of the steps, we'll get into that, is more reaction mechanisms. And it does lower the activation energy. And it can be recovered in the original state. So D is my best answer for question 4. Question 5 is something we haven't got to yet, but let's just answer it so we don't have to keep flipping back and forth. This is a 2-step reaction. This is known as a reaction mechanism. The catalyst is something that you dump in, and then later on it comes out. It doesn't appear in the overall reactions. It starts, you dump it in, and then it comes out. That's a catalyst. So chemical A is the catalyst. That is choice lowercase e, chemical A. Question 6, raising the temperature of a reaction mixture increases the rate of reaction, but does not significantly increase which one of these? Activation energy, that might be it. Average velocity, no, that goes up. More collisions go up. More successful collisions go up. Fraction of the reacting molecules that possess energy is greater than the activation energy. That goes up as well. But the activation energy isn't affected very much compared to all those other effects. 7, in the following figure, which is a potential energy profile, exothermic, how can the interval x be changed in the potential energy diagram? Well, you can lower it by introducing a catalyst. So that will lower it. Okay, here we have a catalyzed and an uncatalyzed potential energy profile. What is that? 80, 90, that's around 93 at the top there. Let's look up in steps of 5. 60, that's 65 there, right? Because that's 70, etc. So the activation energy for the 4 reaction, the presence of a catalyst, is just around 5, right? Because it started at 60 and goes up to 65, so it's around 5. For uncatalyzed, the overall heat of reaction, uncatalyzed, overall heat of reaction, so that's my delta H. So I start with 20. 20 is at the product, 60 is at the reactant. So it's minus 40. Right? So another one here. The activation energy for the reverse reaction without the catalyst. So here I'm going product all the way up to here. So I start at 20, go to 93, so that is 73. So these are kinds of questions you have to answer. And one thing that students forget about is what kind of scale we're using. Every student hates talking about scales of things, but sorry, it's science. You've got to talk about scales. Choose a good scale. So every horizontal line is an increase of 5 units, this time being units of kcals per mole. Okay. So I think collision theory mechanisms, we'll get to that next time. So practice these, read them over, look at some of our curated animations, and that'll be good. So that's the end of lecture 2. Have fun.